Question 9 comes in two parts. First part, we have to show that by using the substitution z is equal to x plus y, that dz dx is equal to z squared plus z plus 1 all over 2z. After that, we need to be able to solve that equation and use that to solve this initial differential equation. So, how do we do that? Well, again, if we look at our equation, z is equal to x plus y, I see an x plus y here, and 2x, 2 times x plus y here. So again, not going to make y the subject and blindly substitute in. Instead, I look for what's the best form of substitution. Second thing I'm going to do is I'm going to find out what is dz by dx equal to, because dz by dx I can get by differentiating this equation, and that gives me differentiate x, I get 1, differentiate y, I get dy by dx, or in other words, dy by dx is equal to dz by dx minus 1. So this is good to know. It means I can say dz by dx minus 1 is equal to bracket z minus 1 times z over 2z plus 1. So dz by dx is equal to z squared minus z over 2z plus 1 plus 1. But again, like with my previous examples, I don't want a plus 1 here because it's not much use to me. Instead, what do I want here? I want 2z plus 1 over 2z plus 1. Then if you look at this equation, what do I get? The whole thing will definitely be over 2z plus 1, but the top line is going to be z squared, minus z plus 2z will give me plus z, and then plus 1. And this is what we were asked to show for the first part. Second part asks us to go on and solve it. So if we look at this equation, this is a simple separable differential equation. So what do? We divide both sides by this expression. That means, rather move all of the z's onto one side, the left-hand side, anything with an x on it to the right-hand side. What does that give me? That gives me 2z plus 1 over z squared plus z plus 1 dz is equal to 1 dx. And of course we know that this doesn't make sense unless and until I put my integration signs there. Now, if I look at this equation, what do I have? This is in the form integrate, this one here, right? This basically says integrate f prime of x over f of x, or rather f prime of z in this case. We'll just make this a bit more. F prime of z over f of z, right? With respect to z. And we know how to do this. Well, you can check this if you like. If I differentiate z squared plus z plus 1, I get 2z plus 1, which is that top line. And I know how to do this one. From chapter 6, I know that this is going to be ln of f of z plus a constant. Right? So let's do this. We get, on the left-hand side, ln of z squared plus z plus 1 is equal to x plus c. Now I know that you're going to tell me, hey Mr. Mark, there is a constant here. Why don't you have a constant here? Well, the truth is I moved it over to the right hand side and coupled it with the constant I got from this integration. So difference of two constants, still a constant, so instead of having two different letters floating around, I've decided to clump them together into just one constant c. So that's no problems. What does this mean? This means that z squared plus z plus 1 is equal to e to the x plus c, but e to the x plus c is the same thing as e to the x times e to the c, right? And e to the c is just a constant. So again, I don't even need that, do I? I can get rid of this, and I can just call this a, where a equals e to the power of c. Now, if I look at this, I'm taking the absolute value of this expression, but I don't actually need to be doing that, right? Because this, if you look at this quadratic has no real roots and is always positive because it's a positive z squared, right? So I can get rid of the absolute value signs, and the next thing I'm going to do in the next line is I'm also going to turn it back from being in terms of z to being in terms of x and y again. So what does that give me? That gives me x plus y squared plus x plus y plus 1 is equal to a e to the power x. And this is our general solution, and we are done.